Okay, thank you. Very, very happy to be here. So as was said, I'm from University of Colorado, Denver. There's actually 3 institutions of higher learning in Denver with all the name Denver, right? So there's University of Denver, private institutions, also Metropolitan State University of Denver, and the University of Colorado, Denver. So if you're confused by it, you're not the only one. Don't worry about it. But I'm very, very happy to present this talk. So Whistler mode waves, the first and future topic of near Earth space sciences. So we'll start by going over a little bit of history as the title suggests, and then I'll try to overall in the talk. I'm not going to go very deep into any specific topic, just only a few equations, I promise, but I want to overall answer the question, why are these waves still the subject of such intensive research over 50, 60 years since they were first discovered? And tell you a little bit about what directions people are taking this research now. So if we go way back in time, over 100 years ago, as in many cases, often technology that develops kind of opens our eyes to many other physical phenomena out there. So back when the first communication systems were, of course, telegraphs. And there were kind of sporadic reports of people sometimes hearing weird sounds on the telegraph. Like that. And when the First World War started, if you study history, you know that there were very kind of static lines, long trenches, and long phone lines along those trenches to communicate. And the enemy would try to actually pick up, the wires weren't often twisted, so the fields would radiate out of those phone lines. The other side would try to eavesdrop on the phone lines. And so one individual here, this Dr. Barkhausen's picture shown there, like some of you here, maybe he was funded by the military-industrial complex of Imperial Germany. So he was working on eavesdropping on the Allied phone lines. And he would notice also that every once in a while you would hear a sound. Get that right. Where the sharing screen next sounds like that whistling sound, right? Some of the non-technical people thought, well, that's the sound of the grenades being thrown over, right? Barkhausen knew it wasn't that. He published, basically tried to figure it out in 1919. Published the first paper right after the war. Revisited in 1930. First, he thought it's an instrument thing, that electronics are going nonlinear. He was able to deduce it wasn't that. He was able to correlate it to lightning, so lightning from thunderstorms, but really couldn't figure out how the lightning, which is an impulsive signal, was making that kind of whistling sound. So what you heard, a whistle, right? It's high frequencies going to low frequencies. So we often look at these things. It's useful to look at them on a spectrogram. So you have time on the x-axis, frequency on the y-axis, and the color gives you the intensity, right? So what you heard there is actually this signal. So this was unsolved for a long time. It actually wasn't figured out until 1953 by this man, Dr. Story. This was actually his PhD thesis. And he figured out that what's happening is lightning is the source of this wave, but the wave doesn't travel along the Earth's surface. It actually goes out into space along the Earth's magnetic field line and comes back dispersed. So it's basically dispersion, different frequencies traveling at different velocities that causes this shape. And why was this so controversial? Well, it suggested that there's actually a significant amount of plasma out there in near Earth space, much higher than was expected before. It was so controversial that his advisor, Dr. Ratcliffe, when he presented this, he said, this is my student's work. It's probably wrong, but it's worthy of attention. Maybe look at this a little more, right? So it's interesting how even his advisor wasn't even sure at that time. Though later, his advisor did honor when he published a book on near space physics, actually put Story's figure on the front cover. So I think he felt that he needs to be redeemed. So anyway, it's that you have electron densities of a couple hundred electrons per cubic centimeter out there along the Earth, and this is a cold plasma. So this thesis not only solved this mystery that was a mystery for more than 20 years, it also described, as some of the many great papers, right? At the end, they describe this thing where they think it's an atom, but it's really a whole new field, right? So describe that there's much more plasma out there, is much larger than could be reasonably expected. We kind of estimated the temperature of it as well. And at the end, in the appendix, he also said there's all these other signals that you can also sometimes hear. So back in that day, right before computers, the way that they would study this, since the frequencies are the same frequencies as in the audio band, they would do a lot of listening, right? So your brain was the kind of the computer fit. You could hear multiple frequencies at the same time. So I'll play you one more recording here. This is when you set up an antenna and just listen.
Earth chorus.
So what did that sound like?
Sounded like the frequency was increasing a lot of those.
Yeah, so you're a very good ear. Yes, it's basically a sequence of rising tones, right? And some people thought it sounded like birds in the morning, right? So it was given the name dawn chorus, and these waves are still called chorus waves. So people talk about magnetospheric chorus, that's the origin. And sometimes you hear hiss waves, and sometimes you hear other kind of whistles. So that thesis kind of set the stage for the whole field of kind of magnetospheric physics, at least when it comes to these types of waves. So what we knew at that point, and now we can have nice spectrograms of this. So we're talking about near Earth space. So the Earth's magnetosphere is the place starting at about 1,000 kilometers above the Earth's surface, where the Earth's magnetic field is the dominant force. So you have the Whistler waves. So those were the first ones discovered, right? So these are from impulsive lightning, and then it becomes dispersed as a Whistler. Sometimes you have kind of broadband hissy-like emissions. Hiss, again, that's what it sounds like that you can observe. These are the chorus waves that we talked about. So as he said, they're short rising tones, and then you can sometimes have some of the waves trigger the others. This is where it really gets interesting. So this is Whistler triggered emission. So you have the Whistler just has this characteristic shape here, and I know the people on Zoom can't see what I'm pointing to, but the Whistler has a shape like this. And here we see Whistlers with now these kind of, when the Whistler comes, it triggers the kind of chorus-like waves. So you have basically wave-wave interactions, or one wave is acting on the particles that are re-radiating the wave. So the physics are very rich. So if we go back to our look at history, so I've sort of brought us into the 1950s, and this was before the space age, right? So this was before any instrument actually was put into orbit to see these things. This was all from ground measurements, which gave a lot of clues as to what's actually going on out there. So at the dawn of the space age, it was understood that near Earth space had a significant cold plasma population, right? So 1 eV or less in those densities that I talked about, a few hundred electrons per cubic centimeter. And there was some hints of hot plasma instabilities because of these natural wave observations. So then we went into the space age, which was an exciting time. As we know, if you write a paper or proposal, if you're first in your field, you can do a simple thing and that's enough, right? So the first satellite by the USSR was basically just a radio transmitter, right? And it was a proof of concept, right? Highly successful. So when the Americans wanted to do it, they knew, well, we need to actually do some science, all right? We need to actually measure something and make some discoveries. We're not going to get credit for being first. So the Explorer 1 actually had much more instruments and diagnostics on it. And it was a big success. It was the first US satellite that was successful after a few failures. So that's why those gentlemen are happy there. One of them is Dr. Van Allen, who designed the particle radiation detector on the instrument. And the big discovery there was there's actually highly energetic particles out there too. That was also completely unexpected. It took him a while to realize that the instrument, it wasn't an instrument effect, the instrument was telling you the truth. So we have high energy electrons. And so by high energies, I mean 1 keV to 10 MeV, high energy ions and protons too. So I think you guys are all plasma physicists here, so you understand the significance of such energy. So that's why the Van Allen radiation belts, sometimes people call them Van Allen belts or sometimes just radiation belts, but they're named in honor of Van Allen, who was the one who discovered them. So there's kind of two belts and a slot region in between them. So a lot of the high energy protons are closer in, and a lot of the electrons are in the outer belt. So we now have, with that, we have this picture of the plasma environment out there. So there's a background cold plasma, low energy, and then there's a trapped hot plasma, right? The hot plasma, or the highly energetic particles, are so such low density that basically you can treat them as individual trajectories. So you can, single particle motion, if you learn that in your plasma physics class, it's really useful for this, right? So they're trapped in this magnetic geometry. So the stronger magnetic field as they get closer forces them to turn around, and they do this helical motion back and forth. So if everything was perfectly static, it would be trapped here for forever. So why do people still care about it, and where do the waves come into the particles? So the reason people care about this, the reason there's actually a lot of funding continued in this area, is that those particles are actually very damaging to space hardware that we put up there, right? It's basically the limitation on lifetime of spacecraft is the radiation from these particles, right? And so there's people who really study the effects. There's there's surface charging, there's deep dielectric charging, and there's actually the really high energy ones just kind of burn through the channel of the transistors, making them inoperable, right?
By radiation from the particles, you mean the actual particles hitting them, not like Bremsstrahl from or something.
Yeah, yeah, exactly. But they have such high energies that it's not a simple question of just blocking them with any hardware. So that's the natural environment has radiation and it's damaging. The natural environment, when you talk about a solar storm, a geomagnetic event, that means that these fluxes are increased and you may lose satellites. Every once in a while you hear like some Starlink satellites were unexpectedly lost, or some satellites were damaged. That's sometimes the natural environment just increasing the fluxes and damaging. What happened? So people like to affect maybe try to control or influence the natural environment. And when it comes to things of this scale, it's just like in your favorite sci-fi movies. The biggest thing we have is the nuclear weapons, right? So after nuclear weapons were developed, there were a lot of tests saying, well, what happens if we launch these up there into space? So this is a picture of one of the last and largest tests, 1.4 megatons launched at 400 kilometers altitude in the Pacific Ocean. It had effects on the power grid all the way in Hawaii, 900 miles away. What it did is it created an additional radiation belt. So basically it hugely increased the amount of energetic particles and their energies, right? And immediately satellites started failing. In the early 1960s, there weren't that many of them. So about half of the operational satellites were brought down either immediately or slowly after, right? Great Britain, the United Kingdom, their first satellite was brought down, suffered on this. They're really proud of it. And the Americans knew why it happened. They didn't tell them right away. One British scientist figured it out, and he had to write a carefully worded thing to the Prime Minister. Why did the satellite fail? It wasn't because they designed it poorly. It was because Americans were doing weird stuff. Shortly after this because the Soviet Union would do it too. And, each time the satellites were getting damaged, they said, well, why don't we sign a treaty and stop doing this, right? This was one of the things that led to the first test ban treaty. So this is not a good idea for anyone. But though this is still a concern for people in the military. So this is a much more recent graph. It's unclassified, but it doesn't have any numbers on the y-axis. Again, I don't have a security clearance, so anything I tell you is public domain here. But this is somebody doing a simulation of a 50 kiloton, so much less than that giant starfish one. 250 kilometers, Bay of Bengal. I guess that's an area of interest. And the point is, in a few days, the number of low Earth orbit satellites really drops, right? So this is something that that people in the military or leadership is concerned about, right? It's a classic kind of asymmetric threat. You do this, you can kind of pretend you didn't even do it, and yet a lot of our infrastructure, we have so many satellites now doing different things that it's a huge threat.
So they don't fail immediately as a result of the blast, but it takes days.
It depends on which orbit they're in, right? So the low Earth orbit ones usually fail the fastest because the higher energy particles are usually.
But I mean, the fastest would be like in a few minutes or seconds. So
yeah, so this is days, right?
Days,
So
right.
so and again, if we assume this is a linear scale, then in one day you're half are gone. Right?
So the nuclear blast creates hot plasma that's been trapped on magnetic field lines.
So that's a little bit outside our extreme, but I think it basically accelerates the plasma that's there to these high energies. So it creates killer
It heats
electrons.
the plasma
Yeah.
that's there.
So and I think you have this rapid expansion of a kind of frozen in field lines that causes this acceleration. Okay, so what do the particles are why some people want to throw money at this problem? How does it interact? What does it have to do with the waves that I initially talked about? So a few slides now on actual equations and maybe for the benefit of the students. So a useful way to understand waves is to look at dispersion diagrams. So if we assume plane waves, take a plane wave assumption. So we say that it's a sinusoid in space and time. And we know electromagnetic waves have electric and magnetic fields. So if you assume everything is a sinusoid, then you really just need to relate the temporal sinusoid to the spatial sinusoid. So you need to understand the relationship between omega and k, and that's really the last missing piece, right? Because there's a sinusoid is defined by three things: amplitude, frequency, phase. So we need to know the relationship between the spatial frequency and the temporal frequency. In free space, like here on Earth, it's a straight linear relationship. So the frequency omega over k is the speed of light. The other useful thing about a graph like this is the slope of this line gives me the speed of propagation. So in our normal everyday, like the speed is the speed of light because the slope of a line is just the ratio of its y value over x value. What happens when we go into a plasma, especially a magnetized plasma, is that direction starts to matter. So no longer do I just, if I impose an electric field, do I get a current along that same direction? I now have the Earth's magnetic field causing this turn, right? Causing basically that a field in one direction causes currents in two directions. That's going to change the dispersion relation. So if you work out the math there, you get that the dispersion relation goes from this simple relationship. This is just kind of what I showed you before, but squared. You get a relationship given here. So where the plasma frequency is how much plasma is there, the cyclotron frequency is how strong is the magnetic field. So the magnetic field, what I'm talking about, is just the Earth's magnetic field. And our simple line goes to three curves, right? Because you have these squares, you have multiple solutions, and the Whistler mode that I've been talking to you about is the one down there. It's a low frequency line down here, so you can immediately tell its slope is a function of frequency. As you get closer to its cutoff, because it cuts off at the cyclotron frequency, the waves actually slow down to zero. it's also a circularly polarized mode. Okay, so the solution is intrinsically circularly polarized, meaning that the wave vectors have to go in a circle, right? And if you think about that, it really has to make sense because what created this was the electron gyrating around the magnetic field. So therefore, the fields have to pretty much do the same thing, or the electrons force the fields to do that because you now have this coupling not only between E and B. You guys are physicists, you like B, not H, right? So E and B, you have E, the currents, and B all coupled together. So the waves are circularly polarized. The electrons are also circularly polarized. That's even simpler, right? That this is physics 2 or physics 1, right? And what can happen is you can have a resonance between the waves and the energetic electrons, right? So the electrons are going at frequency omega c, the cyclotron frequency. The wave has to have a frequency below that. So the way that they can be going around the same rate is by a Doppler shift. Okay, so basically, if they're going in opposite directions, you can get it that the field vectors and the particle go around together. And when anything goes around together, you can have an energy exchange, right? Either the particle can give energy to the wave can give energy to the particle, or both can happen. So that kind of gives you a little bit of fundamental feel as to why the physics can be really rich here. So what's happening in this whole space now is we have the particles, energetic particles, we have the waves. So the waves can affect the particles. The particles can actually, once you have a lot of particles together, maybe they're bunched in phase, you can get coherent currents and you can create more waves, or you can amplify the waves that are there, okay? If we like to think about work in a linear regime, we would say, well, there's waves and the particles amplify the waves, right? That's a linear one, right? If the particles are creating new waves, that's nonlinear, right? So you can kind of decide how deep you want to go in this, okay? What else do the particles do to the waves? Well, they can. What do the waves do to the particles? The particles are trapped. I said if this was completely static system, they would be trapped forever, okay? But if the wave gives the particle a kick, it can cause it to basically go down lower into the earth, where it collides with the upper atmosphere, neutral particles, and it creates usually optical emissions, right? So northern lights aurora is these trapped particles being kicked down into the heights where they give off their energy as light. So that's why you only see it, close to the poles, because the Earth's magnetic field forces that, right? The sun is also driving and pushing on this whole system, right? It does many things, right? There's solar wind coming, there's particles coming. It's also modifying the Earth's magnetic field. So the sun itself usually causes most of the auroras because it pushes the magnetic field. It kind of it drops out some of the energetic particles. It increases the energy of the whole system. So you usually see waves created then, right? So anytime you have something like this with feedback, right? You can spend a whole career maybe studying one of these paths, right? Or you can try to, come up with a self-consistent model, right? Or computer simulation of the whole thing. So there's really a lot of work to be done. It's challenging because of the large scale. So if we move on to, why is this difficult? Okay, there's a lot of feedback systems in physics. Why is it challenging? Okay, one is just the scale and the number of observations we have, right? So magnetosphere is huge. NASA's constantly putting up more great missions, but those are, a satellite is a single point measurement. It's always moving. It measures something. So the background's changing, the satellite's moving. You don't have the full picture ever. So multi-satellite missions are really useful, but there's really just not enough for them to understand everything. As I'll show you in a minute, the propagation of these waves itself is complicated. Okay, so even the simple things like the propagation, without getting into any of the hot plasma effects, is already rich. What we see on the Earth is complicated by the ionosphere, which is this really thicker layer of plasma closer to the Earth. Key processes are nonlinear. And if you want to kind of study this in an active experimental way, saying, well, I'm going to generate some waves and see what happens, which is usually a good idea in physics. It's challenging to generate these waves because of their low the low frequencies. So to give you a little taste on how just the propagation can be complicated. The magnetosphere is anisotropic. Okay, so anisotropic means not the same for a given direction. Okay, what it actually yields is that the way the wave fronts are and the way the energy is going are not the same. Okay, so if you think about waves on the Earth here, which it doesn't matter if I have a wireless wave going any direction in this room, right? It's an isotropic medium, right? Here, so normally you would have that just go straight, right? Here, the waves go this way, but the energy actually goes that way. So this packet actually moves in a different direction from the wave normal. Okay, you can figure out where it goes by looking at this refractive index surface. Okay, so basically the refractive index in free space is 1. The normal to the refractive index is where you will go in the next time step, or where the energy will go. So if it's a circle, it's always the same, right? The radius is always perpendicular to the surface. What happens in the magnetosphere, if you calculate the refractive index as a function of angle from the magnetic field, the Earth's magnetic field, right? You get shapes like this, meaning that if you're going this way, then you're going to change direction. You're constantly changing direction. So I have a video here to illustrate that. If you launch a wave there, it will do something like this. Okay, so if this is confusing, don't look at this. Just look at this first. The black line here is the trajectory of the wave. Okay, so if you imagine a wave is spontaneously generated by nature, or let's say we had a satellite that could launch a wave, the wave would
And the red is the K vector.
The red is the K vector. Yeah.
Can you see it again?
Yes, sure. So the red is the K vector, and the left plot is showing how you calculate where it's going. So it's that refractive index surface, right? It's the refractive index as a function of direction.
And here in this simulation, so is this due to just magnetic field being so homogeneous, or is the plasma also plasma parameters?
It's
like
primarily the
plasma
magnetic field, but you're right that the plasma density, that's what's meant to show in the color scale here. So I guess the Earth is just red, right? But anyway, we have the ionosphere, and then we have decreasing density as we go out here, right? But it's I would say they're both important, but the magnetic field changing is probably slightly more dominant. So in general, the trajectory can be very complicated.
And mostly, it seems like for most of the path, it's almost perpendicular to K.
Yeah, so we say it becomes highly oblique, right? So meaning its K vector is not in the direction that it's going, right?
And it does not really follow magnetic field lines.
No, it doesn't, right? So you gave me an excellent way to do it. So when I started, right, I said this guy's story figured out that the wave follows the Earth's magnetic field.
Yes.
How did that happen? So what he was seeing, this red trajectory. Right? So what happens, and it happens often that people could see often, is that you can have a cold plasma density enhancement along the field line. Think about like an optical fiber, right? So the index of refraction depends on the plasma density. So if you have plasma density that likes to bunch along the field line, you create a natural waveguide or optic fiber to guide that energy, right? So what Story was seeing, and when we see things on the ground, people believe that they're guided in these field-aligned irregularities, right? And if we want to talk a little bit more plasma physics, right? Diffusion coefficients along a magnetic field are always higher than across it, right? So it's natural that if you have any kind of irregularity, it will spread out along the field line as opposed to going across it. So if it was perfectly smooth, so this was decreasing but smooth, the wave would never come back to Earth. So you have this, this is the smooth is complicated. Now you say, well, sometimes there's these guiding things. We don't know how often, or it's really hard to predict where waves go, right? So
did he figure out that the lightning is at a different place So you said that the lightning is over there.
It's
in the
on the,
south.
yes, it's on the conjugate point. It's at the other
Right,
half of
right.
the Earth. Yeah.
And the detector is in the north. So did he understand that?
Yes, and to give you
I
proof,
mean, to give,
I'll even show you the figure from his thesis, right? We show that, and it's good you asked that. because
one has to then know about the lightning over there, right?
Yeah, but what sometimes helps is that, so what, that's the short whistler, right?
Okay,
Sometimes they
great.
come back, so
Okay.
the long whistler, it goes and it comes back. So you can actually have lightning near you
Oh,
and it comes back evenly. It just does two paths, and that happens relatively often. But yeah,
thank you.
no, great question. And so that's, you know, kind of going through the reasons of why this is challenging. Okay. So when something's challenging, you know, we try to do controlled experiments. So there have been instances where people have actually said, okay, we don't want to just wait around for lightning. Let's put our own controlled signal in, right? And if you get enough funding, you can do that. So this is an experiment in the 70s and 80s, where they were able to put kilowatts of VLF power up in along the field lines and observe the waves down there, right? So what's nice about this, it's controlled, right? And what they discovered in this experiment, and this was again repeatable, was that they can trigger the nonlinear phenomenon. Right? So they transmitted a pulse, right? Simple pulse, 2 seconds long at, you know, looks like 1.4 kilohertz, right? And then they waited, or they had people waiting in Canada. What the people in Canada saw was this: they saw the initial frequency plus new frequencies, right? So that's very nonlinear, right? If you put in one frequency and new frequencies come out, that's nonlinear by definition. Okay. So not only was the parent frequency amplified, you had new frequencies created. So these are called triggered emissions, right? The input pulse triggered these additional emissions, and then it actually came back. So it did that same thing we just talked about with the lightning, right? So one hop, two hop, right? So you notice the one hop is much different than the initial, right? The two hop is a little bit different, but has more similarity, right? The coherence of the wave has changed. So you know, an outstanding question is, how coherent does this wave have to be to trigger this nonlinear reaction? Right? And the nonlinear reaction is happening around here, where the wave interacts with those highly energetic electron volt electrons.
So I have a couple of questions.
Sure.
So just want to confirm. So basically, the characteristic travel time for this is seconds.
Yes.
So
It's about 3 to 4 seconds. Yeah.
That's a very human time scale.
Yeah.
And so these waves that are triggered, the additional waves, they are not whistlers, are they? Because I mean, you said that whistlers would decay. Would show on this diagram would show.
Yeah.
Decreasing frequency.
Okay. So very
And here
good.
that's increasing.
Very good. So
Why does it?
I should have maybe been more clear about this, right? So whistlers are the what happens to the lightning, right? Which has that whistling sound, right? But then there's the whole whistler mode, which is just any waves that are propagating in this frequency regime. Right? So these are all whistler mode waves, even though they're not individually, we wouldn't call them whistlers, right? So we would call these whistler mode triggered emissions, right? So the whistling sound gave the whole mode its name, even though they don't all whistle. So, and my whole point of my history lesson was to make that clear, but yeah, as you pointed out, I kind of glossed over it too quickly. So,
And why is there a difference? So here the higher frequencies are propagating more slowly, whereas with a whistler
so they all propagate by the same dispersion relation, right? So this is a single frequency input. So a single frequency you don't see dispersion with a single frequency, right? You will see the dispersion in that if we compare this to this, right? This should be steeper than this, right? So once you have multiple frequencies making the second path, you will see that dispersion, right? But so there's two phenomena here, right? There's a simple one, which is things become dispersed because of different frequencies going at different speeds. And there's the phenomenon of new frequencies being created, right? So what Story explained was the linear phenomena of just frequencies changing. It's just velocity changing with frequencies, right? Nonlinear phenomena is not really fully understood to this day.
So it's a difference between sourcing a single frequency like here, or
Mhm.
lightning, which has a broad frequency excitation.
Yeah. So, okay, let me see. So the other thing physicists like to do is, okay, can we reproduce this on the tabletop or in an experiment, right? So there are efforts in the Naval Research Lab, for example. There's also another experiment in UCLA where they try to recreate these conditions in the chamber, right? So they have a big, nice large chamber here, but it's still challenging, so you have to kind of scale everything up, right? So the wavelengths out there are miles long, right? 10 kilometers, right? So you have to go to everything higher frequency to make it fit in the chamber, right? The problem you run into is you try to scale everything, but what you don't scale is the collisionless environment. So once you start to put things down higher, you can't match the collisionless aspect, right, of that's out there. This is a table comparing plasmas in the ionosphere, the radiation belts, and in the NRL chamber. So you can, and this is their slide. So this is the one they're like, look, we can do it. If you notice carefully though, so this is wave frequency over collision frequency. So this is much less than 1, right? So basically there's or much greater than 1, sorry. So there's very few collisions. This is different. Very few collisions. You can basically say there's no collisions out in space. There are collisions in the chamber, right? So that creates a whole bunch of other things. They also they have different ways of launching waves in there, but they often launch electrostatic waves. It's hard to get purely electromagnetic wisps or mode waves in there as well. The timescales that they do these experiments on, so everything shifted up. Now we're talking about microseconds and milliseconds. So they have to create a plasma, launch waves into plasma. They have to create both the background plasma and these high energy particles, and then launch a wave in it, all in a very short time window. There's walls. Plasma doesn't like to. Plasma naturally will decay, so it becomes a very complicated experiment very fast. Okay, these are some of the results. But okay, so one other thing, and then I'll wrap up because I think we wanted to leave time for questions. So another approach is, okay, the system is complicated. Even if we can't understand it or map it out analytically, let's use machine learning, right? So there are a lot of efforts to apply machine learning techniques. To apply machine learning, you need a lot of data, right? You need a training data set. So what people use is should be written here somewhere, electromagnetic indices, okay? So all these things happening out there, they change the shape of the geomagnetic field, the Earth's magnetic field, right? And observations of the Earth's magnetic field are something we've been doing for hundreds of years, right? Back in the 1800s, there were observatories, countries were proud to set up their own observatories of the magnetic field is measured day in, day out, right? So if there's a solar storm, if there's a nuclear detonation in space, if there's a lot of wave activity, the Earth's magnetic field shows that, right? So by observing on the surface of the Earth, especially in the polar regions, you get a sense of that, right? So that gives you a long training data set. And what they try to do is use, so you get something like this. This is an geomagnetic index. It's basically a measurement of the Earth's magnetic field. This is averaged over many stations around the world, and you can get some time series, right? So they try to basically correlate the time series to observations made by spacecraft, right? And then they claim that they can then predict when there is no spacecraft there, they can predict what's out there. So they are making good progress. These things are getting better, but the weakness I see in it is like you're only going to be as good as the data you train it on, right? So the Earth, your measurements, your long-term measurements are limited to the surface of the Earth. So yes, the Earth's magnetic field does sort of sense that, but it senses in a very subtle and nuanced, complicated way. So can you really tease out all these complicated physics out of that measurement, right? I guess the machines are working on it as we speak. Right? So let me just move to a summary. So happy to take other questions. But my main points are that observations of these waves actually predate the space age. And a lot of people don't realize these days, but it was a way of kind of remote sensing it was the first way of really understanding what's around our planet. And it's sort of amazing that, we knew about the orbits of the moon and other planets, right? The solar system, but we didn't really know about the plasma nature around our planet until the 1950s, right? It's kind of humbling in that way. The space is highly dynamic and damaging to spacecraft, right? So as we put more things up there, this will continue to be an issue. So these issues will not go away. Look to see more and more papers on this thermal mode waves, because there's other effects I didn't talk about, right? There's for those of you who know different plasma waves, right? Also, what's called EMIC waves. So electromagnetic ion cyclotron waves also play a role in this, right? I didn't want to get into those. Those are sort of, they go the other way around. They're a proton wave. But there's other waves. The Worcester mode waves are definitely in like the top 2 or 3 in terms of just being the strongest wave out there. So future efforts include, multi-spacecraft observations are great because we can sense the same waves in space, in their natural environment, multiple points, machine learning, and active experiments, right? There was actually an Air Force mission to put a transmitter in space. That it was a successful mission in the sense that they were actually able to put a high-powered transmitter in space and radiate these waves. Unfortunately, the experiment only lasted a year or 2, right? Which is not really enough. So we all thought in the community they would go for 10 years, but apparently there's some funding cycle or something. Like, okay, we're done. You guys, hope you got your data, right? But so that's I'll just conclude with that. There are exciting hardware experiments being built in the area too.
Thank you. Okay, we're open for questions. Online, feel free just to speak up, or you can write the question in the chat and I'll ask it.
I guess with the machine learning approach, your goal is to you get the signal from magnetic field at Earth, and your goal is to classify that as what the source of that might have been. Is that kind of what they're
or they're even trying to let's just say simpler thing, right? They're trying to correlate that with waves and the energetic particles so that later on they can predict. Their ultimate goal is to predict, right?
Yeah.
Is they can predict what's going to happen tomorrow, right? So they're basically trying to correlate that.
If you had funding, how would you approach this?
So interesting, right? So my PhD was on an experiment similar to the one I showed with launching the wave from Antarctica. Except I did my experiment, we were launching the waves from Alaska. So that's sort of something that's close to my heart because it's controlled, right? So I was really excited when the Air Force launched the spacecraft that was going to do that. And I was kind of disappointed that it lasted so shortly. But I think having some aspect of control, the nice thing, the other thing that really excited me about, especially when I was a student, right? There's the SNR here is huge, right? There's no question you see something, right? It's not like digging out something out of the noise, right? It's like, wow, when it happens, it's really wow. And just to be totally honest, it's not that every time you turn on this, you see this, right? But you see it about 10-20% of the time, right? So I'm a big proponent of kind of active experiments. So because if you're just passively observing, it's you can always match some theory to your observations.
Active experiments in
space.
the actual magnetosphere, not,
Yes.
not in the lab.
Yeah, that's
Not a problem with the lab, but
but
I sort of answered part of my question because I was just curious how reproducible this type of signal is. Was this sort of like a best case example, or was it during a time when, was it during an active period when you expected a lot of energetic particles at the top of the loop?
yeah, no, excellent question. So to see this, you need the energetic particles to amplify it, right? But you also need, remember, the propagation trajectories normally come, you need the guiding, right? And those actually work against each other, because when everything's really turbulent, you have a lot of energy that you can harness, but your paths are messed up. So it was actually the quieting after a disturbance that is correlated with most likely seeing this. So you want the energy to put in there, then you want the environment to calm down so you can get those, cold plasma diffuses along, and now you can see it, right? It may be different if you could do it in space, right? Because if you could do it in space, then you remove the necessity for the wave to be able to come back to be observed. Unfortunately, when they did it in space, they had trouble launching with the waves, remember when we looked at those K vectors and things, right? They launched highly electrostatic waves. And some people said it was flawed from the beginning because they put in orbit a giant electric field dipole, right? And some people said they would have been much more successful with a magnetic loop. But part of the reason it was funded, it was a proof of concept that's such a long boom. And I literally think it was 80 meters long, right? In space. So it was one of the largest objects ever put in orbit. One of the things they needed to hit was to put a long antenna in orbit. So that forced them to go to an electric field, which sort of compromised some of the science, but that's, that's life, right? There's a lot of different things going on, just as we saw with Explorer 1, a lot of different things going on politically, geopolitically, scientifically mixed up, so.
When you say amplified, with respect to what? What does that mean? I assume that
Like a
the signal isn't actually bigger when you receive it than at the source. It must.
Well, that's a good question. Okay, so first of all, if it wasn't, if you think about it, if it wasn't amplified, right, it covers it. It goes over a huge length, right, and there's all types of losses, right, along the way, right. So the fact that you see it at all means it's amplified. If we were to actually look at this is constant amplitude with time. Here it's actually growing in time. So it's actually the longer the signal is, it's growing. So it's actually changing the distribution. It starts in, it changes the distribution, and the distribution feeds on it, right? So not only is it nonlinear in these new frequencies, and for those of you on Zoom, what I'm trying to point, it's not only nonlinear in these new frequencies, it's nonlinear in the actual amplitude itself is temporally changing. Right? So you can actually measure that growth rate. You can measure a temporal growth rate out of these.
So it's sort of like a laser where it goes through active medium and gets amplified. And
Yeah,
the wave goes through.
So people have
This yellow
used that.
region over there.
People have used that explanation and actually call it a maser, magnetosphere.
And let me ask about this. What is the role of Whistler's, if there is any, in this emptying the slot? Is this so? Could you show the picture where there are two radiation belts? Sometimes you have a lot of activity, you fill the entire region, and then the region in the middle, what you call the slot, gets evacuated.
Yeah.
Right. Yeah. Right. Exactly. Why is so?
Excellent question. So there's normally two belts, right? When you have a big solar event, everything gets filled in, right? And so you don't have the two belt structure, right? And then after things calm down, this gap, the slot reforms, right? And so people believe it's Whistler mode waves
from there, but not from the outer belt, for example.
Yeah, so particles, there's something that favorably removes particles in this slot region, right? So people think it's these waves, and the two candidates that are, this is honestly a debate that's been going on for 20 years now. Some people strongly believe it's this His waves, others believe it's the lightning. And sometimes they even say it's the Navy low frequency transmitters that are used for submarine communications that also play a role. So
Really?
yeah. So if you think, we've been climate change, we've been modifying the space weather as well.
I'm not familiar with satellite heights, but do we try to fly satellites in that slot?
They usually they try to avoid what's the picture? Unless they have to, they the low Earth orbit ones are usually flying in this close to this proton belt. They do try to avoid this, right? So it's better to fly outside of it.
And what is the geocentric satellites? They are farther out, and what's the? Is this the scale?
It's roughly the scale. Okay, so this is
geostationary satellites. They are outside of this.
Well, I can tell you how far this is out, right? This is between 2 to 4 Earth radii.
Okay.
From the center, right? So we could figure out.
I think farther out.
Yeah, I think.
So it's 35,000 kilometers.
Okay, so they're going to be further out.
So, but it looks like this slot region is preferred for Well, if there are no other
Except it's not static like this, right? But a key area is understanding why what actually causes the spot to form. Right? So that's something that's.
Just another question. Did you ever mention what is high altitude detonation? When on that slide, did you ever say how high?
How high? Yeah. So high altitude detonation is a few hundred kilometers, right? Or so is the
It's
other.
actually a space.
It's basically in the ionosphere. So the starfish was 400.
Okay.
So the space station, I think, flies around 600. And this one that they were concerned about was just 250, right?
Well, yeah, because if you're on the ground, who cares about the satellite?
This would not, other than like the EMP effects on the power grid, this wouldn't really kill anybody
Yeah.
if you did it, right? Which is why it's kind of, it's a lot of political implications, right? So, North Korea, but we didn't,
Yeah.
what's the problem? We didn't hurt anyone.
If you're on the ground and you see that cloud, you have no more worries.
So if some people think that low frequency submarine communications could be contributing to cleaning out this slot. Are there people trying to figure out how we can clean it? Maybe there will be a coronal mass ejection and we want to eliminate the plasma faster. Is there some big antenna we can turn on that will?
Exactly. That's the dream of DARPA and the military, right? And they call it radiation belt mitigation. So that's what funded my PhD, because you can imagine, we have to learn how to amplify these waves and send them in the right place. That was also what funded the SX mission, which was okay.
So one could do it artificially. One could do cleaning out not just the slot region, but let's say the inner radiation belt. Right?
And so the idea there, the concept would be, and this is way far out, right? Maybe not even in my lifetime, but it would be a special constellation of satellites that can transmit the right signals in the right place to clean it out, right? To make it all come down into just optical emissions, harmless optical emissions.
Do the radiation belts have any known protective property for the Earth? Do they?
No, so
harmful radiation.
the Earth's magnetic field does that, and that's and partly because it traps them, right? So they are the harmful things that the Earth magnetic field protects us from.
So no consequences for just clearing it all that.
Yeah, it protects from alien spacecraft.
Delicate probes that have traveled. So you mentioned the sort of a plasma waveguide forming. So additional plasma has to be created. Is that created by the wave in the first place, or is there another third-party source of plasma?
Yeah, so that's called a duct, right? And kind of like an air duct, right? So they call it a wave duct. Let me see if I have that picture so I can refer to it. Later, okay, yeah. So it can form naturally, or some people have posited that maybe the wave can create it, right? Because if you have any local perturbation of the cold density, right, you can argue that it will naturally diffuse along the line, right? So some people say, well, the wave going up there, if you can create or heat up even more plasma in the ionosphere, maybe cause it to go up, that's a way to create one of these. So that there have been people who have said, if you have high power microwave radiation, you can heat up the upper atmosphere and you may be able to create a duct. And if you can create the duct, you can control where the wave goes, right? So it's a very kind of powerful idea.
And the existence of these ducts were established in terms of not just not just as a conjecture because of the way whistlers propagate, but has it been measured that if they fly a satellite through, you'll see a region of enhanced density?
Yeah, so no, that's a great question. So I would say mostly yes, right? Though it's still, and so they have flown through and they see a change in density and they see a change in wave power, right? But again, the problem with this, with a spacecraft, it flies through and then it's gone. So they see those things co-located. Is one causing the other, or, things like that, because everything changes with its, the index of refraction changes, right? So there's focusing, all the physics change when you change the background plasma density. So I would say mostly yes, right? And it's really the only hypothesis that explains how a wave can start at the ground and come back. So. And it may not need to be, like a duct in the sense, or a fiber that it's, high density, low density, right? It might just be a ledge, right? Even if you have just a sharp enough gradient, you already get some guiding, some surface kind of guiding along there.
How big are these things in terms of like the width?
Okay, so if you take like the classic one like this, it would be less than 50 kilometers wide here. And because, everything follows the magnetic field line, it's going to spread out here to over 100 kilometers. Yeah. So.
Any other questions? If not, let's thank Mark again.